Hi, everyone. My name is Yaron. I'm CTO for a company called Iguazio. Prior to that, I was a VP data center for a company called Mellanox, which deals with high performance. And prior to that, was also CTO for a company called Voltaire, also in the space of real-time and high performance and trading and HPC. I'm going to speak today about how to achieve in-memory performance on cheaper technologies like Flash, but also how do we apply in-memory databases into real-time AI applications. And so I'll start with the first thing, which is sort of the challenge that we see today in the industry. You know, everyone knows this notion of value of data diminishes over time. So we started by analyzing data originally using data warehousing technologies and then batch processing. So results came a bit late. And then we moved into more interactive work through things like Tableau, et cetera, where there was a man in the middle that interpret the results and then act based on those. Now in this age, with everything is connected devices and our kids, the millennials are sort of eager to get responses in their mobile phone immediately, then we need to move into more event-driven architectures where we act on voice, act on text, act on web requests immediately, and hopefully with a lot of data and a lot of context to make accurate decisions. So this is where we're essentially moving into, and this is where we need things like in-memory computing to be able to act fast. Another important thing is here that we had a man in the middle that sort of interpret results, generate reports, and did some actions, and we're moving into more intelligent and AI-driven world where actions are being driven by machines. And that also reduces the latency that we need to, the latency window that we need to react on. Now today when we're doing processing, we essentially have two different technologies for processing data. One technology is more around batch processing, has an advantage of being able to collect lots of data, many different types of data, and analyze them and create aggregates and grouping and some essential insights out of it, but it's extremely slow. And it's not consistent, and it's very complicated if any one of you try to build some Hadoop clusters. On the other end, we have new technologies around stream processing. Those technologies usually observe something, and they're starting to create windows and aggregates. So they have very limited context only to things that went through the same flow. They don't know how to contextualize a lot of data. You know, you're observing some streams of data, but you may need to join that stream of data with operational data like the customer current balance, the weather data in the location of this specific guy, etc. So we need to be able to work or act on a lot of data, be able to contextualize many different data sources when we're acting on the data, especially when we're trying to drive AI-based decisions. So today we have to choose whether we go small but fast, or we go big but very slow. So one of the things to address it is essentially first to address the capacity or the volume velocity trade-off. So today when we go and build traditional databases, this is the architecture of most databases that you'll find, at least the traditional ones. So you'll have some storage layer, and now they'll accelerate the storage layer with things called NVMe over Fabric. You have some virtualization layer, and then you have file system layer, and then you have a database. Okay, and on top of the database, usually you have one specific API for one specific application. You'll have a time series database, or a SQL database, or a NoSQL database. There is a challenge with this architecture because there's too much serialization and too much overhead. Even when your database goes to a file system, and this is based on an Intel research, you do about 7 IOs on a single operation, and that's about, to write 13 bytes, we essentially wrote 28 kilobytes onto the storage. And think about if it's a database, usually does redo logs and undo logs and serialization. So every database transaction maps to multiple file IOs. So that means we have a huge amplification of IOs in most traditional databases. So that means that if we're treating Flash and storage as a traditional file system or as traditional storage, then we won't be able to manage to get to decent performance. So think about today, NVMe Flash, for example, NVMe drives, they are about 500,000 transactions per second, IOPS. but we can't really leverage them in those architecture. Another interesting phenomenon in the database world is that decoupling of layers. This is a slide from Amazon on their SQL database called Aurora, which is a distributed database. And you can see they moved from more of an Oracle traditional approach where you had nodes that synchronize through the storage layer to a three-tier architecture where you have one layer, which is the API and transaction management layer, the second layer, which is the sort of the processing, journaling, state management, and the third layer, which is the capacity. They're not the only ones. If you're familiar with the Azure Cosmos DB, it's also pretty interesting because you can actually apply different APIs on Cosmos DB. You can apply MongoDB API or their own document DB APIs or other things. So we see the cloud providers are moving into this architecture of three tiers of object store as the capacity layer, and then distributed processing layer and caching, and the first tier, which is flexible, more flexible APIs and transaction handling. So with those two approaches in mind, with the challenges that we have with current database architecture and with the trend towards those three-tier or three-layered architecture, let's examine how we can build something which is slightly different. I won't focus on the tiering towards object store, but just those two layers of processing and state management, we can build them a bit different. Because we're not going to distribute it using the storage. We can distribute data across the different database nodes, so we can use direct attach storage. Now, instead of going through file system, doing file IOs, page cache, all those things, we can essentially treat Flash as memory pages. If we go directly to the Flash APIs, we can essentially map all the Flash space as memory. It does have one caveat because Flash is slower than memory. So we can apply trade-offs like using asynchronous IOs, and essentially instead of waiting for the transaction on the Flash to complete, essentially do many other transactions in parallel. But applying this architecture, where we take the database and the database writes directly to Flash through NVMe channels, bypassing the OS, we can essentially get to the same performance of in-memory databases without paying the cost of in-memory databases, because in-memory, memory is about $10 per gigabyte. Most people put about half a terabyte of memory per server. NVMe, today you have 16 terabyte NVMe adapters. You can fit 24 of these in a server. So that means you can put up to 200 terabytes of data on a single server, where using memory you can only put 1 terabyte. Okay? And the performance of Flash and memory is relatively the same. If you put 8 NVMe devices in a server, you have 4 million IOPS. I don't know of any database that does more than 1 million transactions per second. Okay, so we don't have a problem with the performance of Flash. We have a problem with how we utilize Flash. So applying this architecture, if you just take the Amazon marketplace, the different databases of service offerings, you can see that today in-memory databases like MemSQL, Redis, Elasticache, etc., will be anywhere between $10 to $50 per gigabyte. NoSQL databases will be anywhere between $1.5 to $7 per gigabyte for MongoDB service. Okay, and now why is that? Because they use lots of servers, lots of memory for every gigabyte, and even the NoSQL databases are very limited to small amount of few terabytes on a given server. Now, if we leverage the density of Flash, with some of those techniques, we can get to sub $0.50 per gigabyte per month, which is even cheaper than traditional NoSQL servers at the performance of in-memory databases. Okay, so just one thing to think about. The other thing is we don't necessarily have to put a rigid API, and we're going to talk about it later. We can essentially have different APIs on top of the same thing if we use a high-speed, low-latency interconnect as our sort of backplane. Now, high performance, something I've been doing for 20 years, is not just about replacing Flash with memory. There are also other things you need to think about when you're designing for high performance. The first thing is never block. Everything has to be asynchronous. Everything have to happen in parallel. So you're getting a transaction, you're not waiting, you're pushing it to the next layer, you're getting the next transaction in place. You don't use locks frequently, you don't use threads too much. use loops and things like that in order to improve the concurrency and reduce the latency. The second thing is you need to think about avoiding waste of CPUs. And that could be used by doing like predictive fetching of DMA pages or flash pages into memory ahead of time. So when your CPU goes into acting on data, it's actually already in level 0 cache. So those are also techniques that people in real time will use. Other things like avoiding copies and using pointers. It's always harder to program this way, but that yields much higher CPU utilization and better performance. OS bypass, avoiding kernel jumps and things like that. Avoiding threads when you don't have to do that. And the third thing to think about is hardware awareness. So if we have NVMe, and today we can even access NVMe directly from user space, we can leverage that. In order to communicate between nodes on the cluster, what many storage and database vendors do, they use things like RDMA. If you think about Oracle Exadata or even Teradata or some of the EMC storage, they use technologies like remote direct memory access to move pages around between nodes. And also other things that we can leverage in the CPU, vector instruction sets to accelerate searches and other manipulations. So those are some of the ideas you need to think about if you want to get to real performance, because sometimes the benefit of an in-memory database, some reasons why we managed to deliver faster performance on flash versus other people on memory is because we're using many of those tricks that some of the in-memory databases don't leverage. And the latency may actually be in the processing, not in the storage layer. Okay, so let's assume we solve the problem of capacity and volume velocity. Now we have lots of data we can access really, really fast in millions of transactions per second. Does it address the real challenge to deliver real-time AI? Anyone has any idea? What's the sort of the missing piece to, once we have high performance database, we can fetch data at any speed to run our AI logic. So what's sort of missing? Any idea? Okay. Any participation? So I'll give you a hint. Okay. So when you go today to AI, and you go to Kaggle, you go to anyone, sort of 90% of the market is saying that they're doing AI. That's what they think about. Jupyter, Pandas, the advanced ones will probably use Spark or TensorFlow if they're really advanced. Okay, and what they do is mainly playing with machine learning logic in an iterative fashion. So they'll generate CSVs, okay, from all data they've collected. They run group bys and joins and all those nice things. It may take hours. They'll prepare data sets for years, and they'll visualize, and they'll run this loop, okay? But that's very nice for playing games, but eventually we need to apply this AI logic into something productive, like predictive maintenance, fraud detection, product recommendation on the web, etc. And in those playgrounds, we usually think that we have all the data. We do joins, we do group bys, etc. So now we have a feature vector that introduces all the event data, all the aggregates from the last 5 years, all the information about the customers. We sort of in la-la land in that respect. And we can, now when we're trying to productize it, how do we bring all those data, all those variables into the decision vector? Because those variables are coming from many, many different sources, that some of them are aggregates, some of them are operational data, some of them are other data. So that's the real challenge in this area, is how to essentially form a complex feature vector and bring it into the AI decision. And second, once we run the AI decision, how do we take it into an action, respond back in a web page, speed some Alexa sentence, etc. So those are the challenges, the real challenges. So the next thing we need to think about is how to essentially feed all the data from many different sources in different structures. And instead of using joins and group bys that we got used to in the database world, we need to do real-time aggregates. We need to do real-time joining and be able to sort of combine the data, so when the AI decision logic needs to run, it already has things prepared, versus running a query for 2 minutes to gather information and then run the logic. Okay, so we need to think more what we call continuous. So we can feed different data sets through different tools. Some of it may be Spark, maybe through other streaming technologies, maybe through serverless functions. We'll get into it through our custom code. And then we may need to drive results to either dashboards for real-time viewing of the data, or even formulate some actions in the form of pushing to a message queue, responding to a web page, or even issuing a voice instruction. So that's some of the things that we need to think about, is not necessarily looking at batch, real-time, and serving as different silos. Is essentially ingesting data to serve a real-time database, being able to contextualize it from external sources in real time, and be able to serve results to whether it's dashboards or actionable triggers in real time. One of the challenges, again, is that we have many different databases for different types of data. You know, we need a time series database, we'll go to one provider. We need a column database, we'll go to a different one, row databases, etc. So for each one of the databases, you have a different model. And those models, essentially, you can carve it to two different things. One is the indexing strategy that the database chose, and the other one is the data layout that the database provider chose. Okay, so if you're using a time series database, usually it will sequentialize a timestamp, okay, or a parquet file, which is sort of a log structure, will sequentialize the I/O. Now, the reason you sequentialize the I/O has some historical reasons. That because spindles used to like sequential I/O. If you have Flash, you know, that can do about, again, 4 million IOPS on 8 drives, you don't really need to sequentialize anything. You need parallel access to all the different data sets and assemble on the fly. So this challenge that forced us to create different types of data structure for different types of organization has a lot of roots in legacy. If you think about even Cassandra, okay? Cassandra does log structure merge tree, which is trying to solve disk spindle challenges of sequentializing I/O. In Flash, you don't need log structure merge tree. Okay, another thing we discussed is indexing. So usually you have two types of databases, like Redis or Memcache. They use hashing. So that's very good for ingestion. I could go hash some key, right directly to the same place. Traditional databases use B-trees or other forms of indexes. So they're very good at scanning, at searching for certain data. Other things are even more optimized for scan operations. So if we can sort of come with a multi-dimensional index strategy that we can essentially have hashing and trees and graphs or pointing to the same data, that means that we can do real-time ingest, real-time fetch, in parallel to doing scans and searches on the same data. So essentially, the architecture that we came with is having three-dimensional keys and dynamic structures that can form any type of data, whether it's files or objects or tables or columns or time series, etc. And I'll show you one example why this could be useful. So everyone knows time series organization. So let's assume I have time series data, you know, traditional, have a device, has bandwidth, you know, MAC address, port, etc., networking device. Usually I have things that I will refer to as labels. They're coming again and again. And there are things which are the actual data in a time series data, okay? So I can go and put this in Cassandra, and we've seen people doing that and ending up with 500 terabytes of data. Why? Because they want to run SQL query across each one of those dimensions, okay? Or I can deduplicate the data and compress the data in an organization that will be significantly faster and cheaper. So in this data organization, for example, I took all the things which are labels, I placed them only once, and then the data, I wrote it into two different mechanisms. One is sort of a column organization, which is using Gorilla compression, which is extremely dense time series compression invented by Facebook. Another one is pre-aggregates, so array structures that store, for example, hourly average, hourly summary, hourly standard deviations, etc. So that means that today, when I run a query, first I'll only fetch few lines. I may even be able to fetch them through random access if I'm only looking at a single matrix. If I need a bunch of matrix, then I'll need to fetch a few lines. Based on the granularity of my search, I would either go to array organization or blob organization, and that organization essentially allows me to provide real-time consistency because every update is random. Within a millisecond or less, it's up to date. It has 50-to-1 compression ratio based on use cases that we've looked at, which ranked 500 terabyte to 10 terabyte worth of data compared to Cassandra. And it's about 10 to 100 times faster queries. Now, this is allowing you to do the same on the same structure because if I created a flexible schema, now I have a data type which is a compressed blob and a data type which is an array and a data type which is just a traditional attribute. So this is just showing you the value of now when you have the combination of random access, different keys, and different data structures within your database, you could do very interesting things. Now, some of the challenges is not all those things are structured data because people now want to talk to machines, they want to send SMS messages to machines. So we need more flexible computations or the future of stored procedures. Okay, so the next thing we came up with is when you're developing code, then there's a bunch of other things that you need to do to make it really work. Okay, you need to compile it and build a Docker image, and need to instrument it for logging and monitoring, etc. And then provision some servers and OS and patching and security and all of that. So some people came with a nice idea called serverless. Yeah, Amazon came with their sort of Lambda architecture, and that allows you to write the code, run some local testing on your code, on your IDE of choice, then provide some spec which says, okay, I need this amount of CPU or GPU or memory or other things, and push deploy, which will trigger an automated provisioning, and your infrastructure of choice of cloud provider will provide all the logging, monitoring, provisioning, etc. So this is, if anyone knows Amazon Lambda as an example? Okay, good. I see some nodding, so we're progressing. Cool. But Amazon Lambda is not really designed for the kind of concurrency in real time that I'm talking about, because it's really slow, only about 1,000 events per second. So what you need to do if you want to get a real serverless that will fit into data processing or AI is address three main concerns, okay? One is performance. The other one is ability to run distributed data processing, so streaming and batching workloads. And the third is ability to actually access state or databases or storage and maintain some caches. All those three are things that you can't find in Lambda, so we've came with an open source project called Nuclio. It's now becoming more and more adopted. Contributors include Microsoft and others, about 2,000 and something GitHub stars. So this is currently one of the leading serverless frameworks that also has those attributes that can apply to data processing. So it can do about 400,000 events per second compared to about 1,000 in Lambda, using a lot of real-time technologies and parallel processing, etc. It knows how to work with any data source. So you can write a function once, and it's using a new standard that we formed in the Cloud Native Foundation called Cloud Events. So I can essentially feed the same function from Kafka, Kinesis, RabbitMQ, MQTT, everything without changing my code, because there is a standard event signature that's fed into the functions, and it automatically knows how to deal with checkpointing and redistribution of shards. And the last thing, it also knows how to bind dynamically to databases and store state. So this is really allowing you to deliver data processing tasks. So instead of using rigid stored procedures in a database, now you can run in any language, any one of those 7 languages supported, and you could do all those things. So now if I take a use case of traditionally taking some data, ingesting it, the first thing I'll do is essentially alert, compact the data, index it, organize it in some database. Now I may take multiple sources of data. Maybe I'll take a Twitter feed and examining a stock to analyze sentiment, and I put the results in a table. And those things will essentially enrich the data and contextualize it. And then when I run an AI logic, I need to do sort of a real-time join on all those different data points to form my multivariant analysis. Some of the data points will be pre-aggregated, so my query of fetching and forming this vector will be really fast. And then after I've done that, I haven't done really much. I need to do something with the data. So there are two ways of working with the data. One is generating triggers through message queues or any other form. And the second one is to serve the data through real-time dashboards. So if you are trying to form sort of a real-time analytics pipeline, that's usually how it needs to look like. So ingesting, sometimes we'll do alerting immediately during the ingest because we already identify failure. We need to enrich and contextualize the data to form a deeper knowledge, essentially. All this knowledge vector needs to feed into some pre-baked, pre-learned algorithmic AI model. Sometimes we use reinforced learning. If you take stock prediction, for example, if I learned yesterday and now the market behaves a bit differently, I have to incorporate the behavior of the market today into my decision. So you have AI algorithms like RNN and others that know how to combine fresh data and fresh models with historical models. So that's the general idea. So looking at the use case, okay, how do we build all this into something useful? This is an example of a project we had with the telco. We have several deployments of the same solution already in different places. But this telco wanted to listen in real time on all the different data points that they had from the network, net flow data, firewall data, et cetera, to be able to analyze two different things. One is what's the status of the networks and to predict potential network failures. That could cost them a lot of money. And the other one is to identify security attacks on the network and its impact on its customers, okay? So essentially, they feed a lot of data from many different places. It all has to run in real time. They have to run predictive logic, which gives them prediction of which areas of the network are going to fail when, according to the current model, including visualization of all of that. And also, when there is a potential impact on failure, they're interested in knowing how much is it going to cost, because maybe I have probability of 2 failures in different probability, but that's going to cost me $1 million, and that's going to cost me $5 million. So maybe the thing that has lower probability I'll prioritize first because the impact on business is bigger. What's impact on business? It's essentially combining data from operational data sets that I have on customer data, what they've paid me, for example, last month. So that means that I had to deal with joins in real time of operational data with historical data. That's not something that you can do on stream processing. That's why you really need some context in a database. So those guys had the choice of how to build it. Okay, the traditional approach looks like something like that. You have the real-time layer, Kafka, Spark streaming, etc., storing state in server database, and then you have some real-time visualization, doing the same on batch, Hadoop, etc., creating some models, 2 worlds that don't connect. There's no actions involved. It's just visualization, just people looking at things. There's nothing automated. There's a huge skill gap to build such a thing. And the alternative that we came with is essentially having sort of this unified real-time data with functions, custom functions that know how to parse the NetFlow data and other network data and do aggregates and ingestion in real time, running Spark for running on the enriched feature vector and creating predictions, serving the data and triggers through other functions, all in real time in a continuous fashion. There's no batch processing here. Everything is up to date always, and you can access through the same dashboard. You can access the data from today and the data from the last 3 months. I'll take the same example for a use case in IoT and manufacturing. So this is a joint solution we've formed together with Microsoft, with Azure, because again, they went to factories and they said, go to the cloud. The factory said, yeah, we have video cameras, we have sensor data, SCADA machines. We're not going to send all the data to the cloud just so you can analyze it. So let's come with a solution that combines the capabilities of cloud in generating machine learning models and aggregating across lots of data, but also acting at the actual factory. So again, you have sort of a unified data layer for storing all the information. The first thing that you have is a function that intercepts SCADA telemetry or machine telemetry. That thing needs to ingest and organize the data already pre-aggregated, because the machine learning models, they don't work on raw data. They work on standard deviation. They work on statistical models across windows of time. So essentially, we're aggregating the data in real time. We may identify alerts immediately because the machine says that there is a problem. So you don't need to be too intelligent to trigger on that immediately. You can then run another function which is preloaded with a machine learning model, whether it's TensorFlow or Spark or H2 or any other, or even Pandas-based model. The logic here in this function has to join information from the statistics, from environmental data of the factory, from machine learning model that was pre-learned in the cloud, and other machine metadata. Like, for example, one was the last time it was serviced. Now, all those different data points have to arrive to the same machine learning model when you're doing the actual inferencing to be able to drive a prediction alert. Now, the other challenge is we need to move data back and forth from the cloud, because every time we learn some data, we form aggregates, we want to send those aggregates to the cloud so the machine learning model will become more accurate. And every time the machine learning model gets up to date, we need to trigger those appliances to essentially load the new model into the system and restart the machine learning models with the new model and the new processing code. Now, all of that may also have access from local dashboards that just want to visualize the current state of the machines. Okay, so using this architecture, again, you have a fully continuous flow. Nothing here queries, and works in a static fashion. I'll show you another last example, which is based on a sort of a hackathon that we did, but it's a real customer problem that we got. Everyone likes to run SQL queries against database, but we really wanted to talk to the database. It's more interesting. So what we have is real-time data feed coming from cars, telemetry information from cars. This data is also going through a machine learning process. And then, in order to make it a little more interesting, we have voice queries sent to a function, aiding with using also Google Dialogflow, which is the equivalent of their Alexa service. And this function translates the text, the speech, into SQL queries, respond, and then when you have the results of the SQL query, we're pushing those as voice and as image video. Okay, so that's a big challenge. By the way, it took about 1.5 days to develop it. And I hope it's going to work. Just a second. This is on real-time data.
412 of 1384 drivers are busy at the moment. That's 29% of them.
Can I see the list of drivers?
Here they are, starting with Ruby Naquin.
What about our income totals in the last week?
Looks like you made the most bank on Sunday, with around 18,600 bitcoins.
And how much on average did this cost each customer?
Here you go.
Okay, thanks. So what you saw in this application is a real-time feed, and I had real-time voice-activated queries on the building on aggregates that are built on the real-time feed. And no one noticed even a single glitch of sort of latency or something like that. So that is how we can build some of those solutions. So yeah. Sorry. So to summarize, and by the way, I also mentioned Bitcoin. I didn't have Bitcoin throughout the entire presentation, so just so I'll have complete all my buzzwords for today. But what you could see is that using this approach, we need to stop thinking about databases as something that we just like query and the answer, you know, and we pre-aggregate and we do joins and we do all those things. We need to address two key challenges. One is the scale, because we need to address a lot of data and be able to access it in real time. That's one thing. The second thing, we need to be able to do pre-aggregates and do sort of combining data and grouping data and all those things, so we can have real-time access to those aggregates that we need to feed into the AI logic. And in many cases, we have a lot of different types of data, so having a data organization that allows us to store all those different types of data, streams and time series and columns and rows in the same place, and be able to do a single join across all those different types of data is very powerful, as you can see. So that's the end of my talk.